Now, the loop that was rotating in a region where there is a magnetic field is acting as a voltage generator. It's generating electricity for us. It's supplying power. Now, remember that power is given by this expression. P is equal to I times V, current times voltage. Now, if we connect, like in the simulation that we looked at here, if we connect the generator to a resistor, then the power dissipated by the resistor is going to be I times V. Okay, but when we use this expression, we were thinking of DC power sources, where I is constant and V is constant. That expression is still appropriate, however, it's appropriate for a change in current and a change in voltage. In the case of a resistor, if the voltage is going to look like this, then the current is going to be given by V over R using Ohm's law, so the current is going to look somewhat the same way. But of course it's a different scale. Now we are talking of the scale of the current. So we are, if I was going to graph this, probably I'm going to have to add another scale here for the current. This is the scale for the voltage and that's the scale for the current. Now you notice in this case, when the voltage is positive, the current is positive. When both of them are negative, when the voltage is negative, the current is negative. And we're multiplying both of them by each other. Now, if I multiply a negative number by a negative number, we get a positive number. We multiply a positive number by a positive number, we get a positive number. Now, again, this expression, I times V for the power, is going to work all the time for every instant. The power dissipated at this instant is going to be this value of the voltage times this value of the current. The power dissipated at this instant is going to be this voltage, which is 0, times the current here, which is 0. The power dissipated at this instant is going to be this voltage times this current. And what I'm trying to stress is the power is not going to oscillate between positive and negative. It's going to change values, but it's going to change values in this kind of fashion, remaining always positive. On average, okay, if we are doing calculus, we can show that here, but on average, the power dissipated is going to be given by this expression. 1/2 of V max, which is what we are showing here, times I max, which we are showing here. That's the power dissipated on average. The instantaneous dissipation of power changes according to a curve that looks somewhat like this. Now, because of that, we define something, what we call the root mean squared. Average, remember, is a mean. What we define as the root mean squared is V max over square root of 2. Okay, I should have written it, V max over square root of 2. Remember this expression, what do we have here? We have 1/2. Okay, I'm going to rewrite it there. So what we have for power, we said V max, I max over 2. I can rewrite that as V max over square root of 2 times I max over square root of 2. Now, what this leads me to, V max over square root of 2, using this definition here, we just call it VRMS, V root mean squared, and I max over square root of 2, you guessed it, we call it IRMS. Now, multimeters that you use in lab, that's what they measure for us. They cannot measure the instantaneous value of voltages, they measure some kind of an average. And that kind of an average is going to be related to the root mean squared values, Vmax over square root of 2 and Imax over square root of 2. So the power expression for a sine wave voltage is going to be IRMS times VRMS. Now, one last thing, kind of a summary. The expression for the EMF generated by a loop going around in a magnetic field is given by omega, which is something that we determine since we are the ones who are going to spin the loop, times A, the area of the loop, times B, the magnetic field we subject it to, times sine of omega t. Notice, since we determine omega, we determine the sine function. When is it maximum and when is it minimum, etc. This leads me to writing it in terms of voltage, Vmax times sine of omega t, where Vmax is omega A times B. And remember, we determine A by choosing the size of the loop. We set the value of B, and we set the value of omega. Okay, one last thing. We discussed the voltage that we induce in the loop just by spinning it around in a magnetic field. And because of that voltage, if we connect that loop to a circuit like we had this, so it's connected to a resistor, so we have an actual flow and current. Because of that flow and current, the loop itself is going to experience a magnetic force. Remember what we have discussed before, a loop carrying a current in a magnetic field. So because of these forces that both of these sides are going to experience, then the actual loop is going to experience a torque. That torque then is ABI sine theta. Now, of course, if we have a certain more than one loop, it's going to be NABI sine theta. Now, anyway, a little rewrite by putting I here in here, that gives us this expression. Now, however, the most important thing to remember here, what does that torque do? It's going to oppose the change in flux. So as we try to spin it, because of this current, it's going to become harder and harder to spin the loop. So we must supply an external torque, an external energy to make the loop continue to rotate with the right speed and continue to provide energy. So that's conservation of energy. And that's an interesting concept. If the generator is not connected to the grid, it's going to be easy. It's going to be easy for us to spin it around. The minute we connect it to the grid and we start having a current flow, then we are going to have a current in the loops. They are going to experience a torque. So we have to overcome that torque to keep it rotating at a constant velocity.